I didn't see you there. I just got out of the shower, and I was thinking about Goldbach's conjecture. Just kidding, this is obvious costuming. My hair is not even wet, and my thoughts don't magically appear on this chalkboard. But it is true to say, I just put on this bathrobe for your enjoyment, and I want to teach you about Goldbach's conjecture. I wish that this could be one of those videos where I show you a cute little proof of a cute little theorem, but unfortunately this is an unproven conjecture, so we're just going to chat. We'll just shoot the breeze a little bit about good old Goldbach. Let's take this off, it's a little silly. So, this theorem has really fascinated me since I was an undergrad. I first found it in a discrete math book, and by found it wasn't some great discovery, it was right there, written on the pages. And what fascinated me was that I had just been learning about proofs and dealing with prime numbers and integers, which are the friendliest of proofs, and go figure, that's why I became a number theorist. They seem so approachable and so pretty, and this one is no exception. Every integer greater than 5 can be written as a sum of 3 primes. That's cool. What this comes down to is that we can just add up some primes and get something. And there are so many different ways of doing that, it seems really quite obvious. In fact, if we count higher and higher, the number of ways that we can express an integer as a sum of 3 primes gets larger and larger. Let's see some examples. Alright, greater than 5, so 6. 6 could be written as 2 plus 2 plus 2. 7 could be written as 2 plus 2 plus 3. 8, well, we can't go 2 plus 2 plus 4, because 4 isn't a prime, but we can do 2 plus 3 plus 3. 9 could be written as 3 plus 3 plus 3. It could also be written as 5 plus 2 plus 2. 10 could be written as, let's see, 2 plus 3 plus 5. Do we have any others? Let's see. 3 plus 3 plus 4 doesn't work. 2 plus 2 plus 6 doesn't work. 5 plus 5, and we're already there. So yeah, I think this is the best we're doing for 10. 11 could be written as 3 plus 3 plus 5. Let's see, anything else? 2 plus 2 plus 7. Let's see, we could do 3 plus 2, but then we'd need 6. We could do 5 plus 5, but then we need 1. Careful, 1 is not a prime. I think that's probably good for 11. 12, we could do 2 plus 3 plus 7. We could do 2 plus 5 plus 5. Let's see, 7 plus 5, and we're already there. 5 plus 3, and we need 4. Starting to notice a pattern here. All of these evens are going to have to include 2. Every even number is going to have 2 as one of its primes, because all of the other primes are odd. So we're going to need to get to an even number somehow. 2 odds and an even. It's the only way to go. So basically we're looking at ways of making 10 out of 2 primes, and then adding 2. That's a lot easier to look at. In fact, there's an equivalent form that just talks about all of the even numbers and all of the odd numbers. There are a lot of different ways of writing this. One of the ways we could say this is the odd numbers can be written as 3 primes, the even numbers can be written as 2 primes, right? That's basically the same thing. But the other thing that we're noticing, like I said, at first we were only getting one way of writing them. Now it seems like 2 is kind of the norm. Once we get up to 13, well, we're going to have 3 plus 7, 3 plus 5 plus 5. And then let's see, do we have anything else? We could do 2 plus 2 plus 9. 9's not a prime. Okay, 13 seems like it's got 2 ways of writing it. These are going to get bigger, and that pattern continues, but look at 10. It's not like it's just a steady increase. It's not like just because a number is bigger, it's going to have at least as many ways of writing it as the sum of 3 primes as the numbers before it. There is going to be a little bit of wobbling. There are some cool graphs that you can see which show how many different ways you can write something as a sum of 3 primes. The problem is they don't go to infinity. Nothing ever does. And so as mathematicians, we're not satisfied with just knowing that this conjecture holds with all primes or with all integers from 6 to a googolplex. We need to know it holds for all integers, and that's what hasn't been proven yet. There's something called proof by exhaustion, where if the theorem was from 6 to a googolplex, we would be done, because we could just show literally every possibility, but we can't do that with infinitely many integers, and there are infinitely many positive integers. So there's still some work to do, there's still some thinking to do, and as much as this seems incredibly intuitive, it's not as easy as it sounds. The primes are tricky beasts. That's sort of the whole point of number theory, is the primes are tricky beasts. So I thought this was cool. I hope you do, and I hope you forgive me for lying to you about the shower.